Righto, the last thing that we need to go through in this topic is how to actually calculate pH. Because pH gives us an indication of whether something is a strong acid or a weak acid. It also gives us an indication of its concentration, quite often, I should say. It's based around a couple of key calculations, which are actually the same calculation as each other. They're just the opposite of each other. We have the pH of a solution is equal to the negative log base 10, which is just the log button on your calculator, of the hydronium ion or hydrogen ion concentration. If, however, you're given the pH and asked to find what the hydrogen ion concentration is, all you do is go 10 to the power of, that's that little triangle, or half triangle, negative pH. So I'll show you how that's worked out with acids in a moment. There's another really important relationship, and it's based around this equilibrium. Oops, I break it through that yet. And this is called water dissociation. And water dissociation, as you can see, is an equilibrium, which means mainly, the rate of reaction is the same in both ways. Under standard conditions, this has got a particular value, 10 to the power of negative 14. And it's called Kw, W for water, K because it's an equilibrium constant, all right? And that's what basically we're going to use. This is also equal to the concentration of hydronium, or hydrogen, times the concentration of hydroxide ions. The reason that we don't put the water underneath it, divided by the square root of water, water squared, is that there's still water on this side as well, technically. So the amount that's dissociating, its concentration stays at roughly 55.5 moles per litre. So if it's the same concentration on both sides, it cancels itself out. It doesn't really change enough to be included. All right? So this is the maths behind what we're going to do today. So this is the theory and the maths behind it. What I'm going to need is for you guys to do some calculations for me to help out with this. The acids that we use in the lab are normally strong acids, or inorganic or mineral acids, such things as HCl, HNO3, and H2SO4. What this means is that they fully dissociate when we put them in water. So if I was to show you HCl being put in water, then it wouldn't be an equilibrium. It would be HCl plus H2O goes to, so these two aren't there anymore, H3O plus, which is the conjugate acid of water, and Cl minus, which is the conjugate base of the hydrogen chloride. Just a quick note about that. Even though it's called a conjugate base, it's not alkaline. It's actually got a pH of 7. But the H3O plus has got a pH, depending on its concentration, it's going to drop the pH considerably. So let's say, for argument's sake, that we've got a 0.5 mole per litre solution of HCl. There's actually no HCl particles in that. They've all turned into these two. We can see that everything's in a 1-to-1 ratio. So that means if it was 0.5 moles per litre, it has got 0.500 moles per litre of hydronium ions. So therefore I can use one of those equations up on the right hand side to calculate the pH of this solution. This is where I need you guys to be my helpers. I want you to type into your calculator the negative button, then the log button, then I want you to put in 0.5 and then equals, and tell me what we get. 0.3 roughly, isn't it? Okay, so you'll notice that that is lower than 1. So when we told you that pH goes from 1 to 14, we're not strictly correct. Okay, it can go outside those values. It's just very rare for it to do so. But 0.5 moles per litre HCl doesn't sound particularly nasty. We use 2 moles per litre in the lab. So, it's quite a lot more dilute. Yet its pH is as low as 0.3. Now, I just want to quickly go through something quickly with you here. And that is to look at a bit of a trend. We're going to do the hydronium ion concentration here for a couple of things. So this will be our acid concentration, and we're going to do our pH over here. And see if we can see a bit of a trend happening here. So let's say that our hydronium ion or HCl concentration was 0.1. Do the same process and tell me what we get for our pH. 1. We'll go 1.0 there. I should have a 0 there. What now if I had 0.01 as my concentration of my HCl? 2. What's the other way we could write 0.01, say in standard form?
1 times 10 to the negative 2.
Fantastic. So this is actually the same as 10 to the negative 1. This is 10 to the negative 2. So 0.0010 would be 10 to the negative 1, 2, 3. Without using a calculator, who'd like to predict what that will be? 3. Cool. What if we had 10 to the negative 12? I'm not going to draw that because it's too many flipping zeros. So what do we guess the pH might be?
12.
12. Excellent. So that's going to be a base. So you can see the numbers got so low. This is 11 zeros, then the 1. So it's so tiny that its pH is 12. That would be a strong base. Right? So that would be something with a pH, it'd be a base like sodium hydroxide with a concentration of 0.01. And the reason I know that is the next thing I want to show you. Alright? Just quickly by the way of the calculators, go 10, and then you should have a little button like that to the power of, and then negative 2 equals, and you'll see that it ends up being 0.01. So that's how we go that way. Alright. The next thing, which is really, I think, the hard one, is bases. And we'll put that over here. Bases can be done a couple of ways. But the best way to do it is to use this equation, this relationship here, and rearrange it. So we'll turn it into a little triangle to find the hydrogen ion concentration. So the way that I like to draw this one is that 10 to the negative 14 is on the top of my triangle, and then I've got H3O plus and OH minus on the bottom. I'm hoping that'll fit in the, just. And I'm always trying to find hydronium. All right? I'm always trying to find this. That's what I want to find first. Okay? So, if I give you an example. Sodium hydroxide. Let's say I've got that dissolving in water. So I have NaOH, and in this case I actually can put the water on the top, and it turns into sodium ions and hydroxide ions. Let's say I've now got 0.5 moles per litre of sodium hydroxide. That means I've got 0.5 moles per litre of hydroxides. Okay, well, that means that I now know this number here. I've got this number here is 0.5. So now on your calculator, could you please go 10 to the negative 14, which by the way is 1 exponent negative 14 if you prefer using exponents, or it is 10 with a lower o negative 14. Okay, so 10 to the power of negative 14 divided by 0.5 equals, and tell me what number you get there, please.
2 times 10 to the negative 14.
Okay, 2 times 10 to the negative 14. So hydronium ion concentration is equal to that divided by that, and as we've just said, is 2.0 times 10 to the negative 14 moles per litre. Now I've got that number, I can go, don't take it out of your calculator, I can go negative log answer equals, and I should get, just at a guess, 13.7.
Yeah.
Okay? And the reason I know it's 13.7 is that this number plus what's called the POH, okay, so the P function for the hydroxides should add up to 14. Okay? But more importantly, that process shows us that that times that will equal 10 to the 14. And that's always true. That will always be the case. Okay? So that's the maths behind what we have to now learn about acids and bases. The hard questions are when you're given a base. And just remember this triangle, and remember you're always trying to find hydroxide, and it should make this quite an easy process to do.